Okay, we're going to talk about inverses. So this picture inverses. So notice that the x's for the original relation was 0, 1, 2, 3, and 4. And the outputs were 6, 4, 2, 0, and -2. So what an inverse relationship does is just switches the x and y's. So notice the x's now become the y's of 0, 1, 2, 3, and 4. Right? So it basically switches the domain and range. So write that down. An inverse relation interchanges the inputs and the outputs, basically the input and the output values. All right, so the domain and range also switch. So if I had, let's see, if I had some function and my inputs were 1, 2, and 3, and my outputs were A, B, and C, then the inverse of that would be, so my x's now would be A, B, and C, and my outputs, or the range, would be 1, 2, and 3. So it just switches them, right? The x's and y's switch. So for example 1, we're going to find the inverse of this. So since the x's and y's switch, the domain and range switch, we are going to, if you're a step person, this is for you. So we're going to switch x and y, and then solve for y again. So we have this example of y equals 3x minus 5. So step 1 is to switch x and y. So I have x equals 3 times y minus 5. Okay, so I switched x and y, and then we're going to get y by itself again. So I will add 5 to both sides. Those aren't like terms, so I just have x plus 5 equals 3y. And then I'm going to divide everything by 3. So my inverse relationship is y equals 1/3 x plus 5/3. Right, that is my inverse. All right, so our next, our key concept is, so the one thing that you need to know is f inverse. So f to the -1, it's not a negative exponent, it's just meant as the f inverse. So if we have a function f of x, the inverse of that would be f to the -1 of x, okay? So this would be our function, and this would be the inverse of the function. So just a little terminology for you. And also how we can prove that a function and its inverse are in fact the inverse in the function is if we compose them and we get x, and then we compose them again, going the other direction, we also get x. So we'll do an example like that. Right, so we have f of x, we have our inverse. Right, this is the example from 1 where we found this inverse. All right, so we're going to compose them. So we have f of f inverse of x. So remember, that is the same as, instead of f of x, this is our new x value, this thing. So we're finding f of 1/3 x plus 5/3. Okay, so that's our new x value. So our f function is 3x minus 5. So I'm going to replace x with 1/3 x plus 5/3, and a minus 5. All right, so that's our f function, and then our new x is this. Okay. And then we're just going to distribute that and simplify. So I distribute this, so that's like 3/1. So we multiply the fractions, top with the top and bottom with the bottom, which is 3/3, so that's just x. 1x is x. And then this would be plus 15/3, and then we still have the minus 5. Okay. And if we simplify that even more, we're going to get x, 15 divided by 3 is 5, so we have 5 minus 5. And so 5 minus 5 is 0, so we do get x. All right, so that one checks out. And then our next one is to go in the other direction. So we have f inverse of x, which we're going to plug in f of x. So that's the same thing as f inverse, and our new x will be 3x minus 5. All right, that's our new x, so we're going to plug that in where the x is. So, and our function for the f inverse is 1/3 x plus 5/3. Okay. And so our new x is 3x minus 5. So we're going to multiply the fractions again. And so when I do that, I'm going to distribute. So this is 3x over 3. And 1 times negative 5 is negative 5. And 3 times 1 is 3. And then plus 5/3. Right, so when I simplify that, 3 over 3 is 1. So this is 1x or just x. And then negative 5/3 plus 5/3 is 0. So in the other direction, we still get x. So we can verify that those are inverses of each other. Okay, our next example, so pause it, figure out what's going on, and then unpause, and we'll see if you and I think the same thing. All right, so we have this elastic band, and we're going to find the inverse. But let's figure out, so R is the resistance, and that's in pounds. Okay. And then L is the total length. If word problems are confusing, it's helpful to just kind of write down what the labels mean. That kind of helps you familiarize yourself with the problem. And then it's modeled by this equation. So R is equal to 3/8 times the total length minus 5. Right? And then we're going to find the inverse of the model. So one thing to note is you don't switch the variables for inverse models. So we're not going to switch L and R and solve for R again, because then it gets confusing about what we're solving for. So we're just going to get L by itself. So what we're going to do is we're going to add 5 to both sides. So we have R plus 5 is equal to 3/8 times L. We can multiply everything by the reciprocal, or if that's confusing, we can also just take it in 2 steps. Right now, it's 3 over 8, so we're going to multiply both sides by 8. So when we do that, these 8s reduce out. 8 over 8 is 1. So on the right side, we just have 3L. And on the left side, we have 8R plus 40. And then to get L by itself, since it's multiplying, we're going to do the opposite and divide everything by 3. So now we have L is equal to 8/3 R plus 40/3. Okay, so that is the inverse. So we just solved for the total length. Right? All right, so we found the inverse, and now our goal is to use the inverse function to see the length when it provides 19 pounds of resistance. So 19 is going in for R. So I use my inverse function. So in R is equal to 19. Okay. So we have the length is equal to 8/3 times 19. Right, and then we can do that 19 over 1 plus 40/3. All right, so our length, let's see, 18 times 9 is 152. And then 3 times 1 is 3 plus 40/3. And since I have the same name, I keep that name, the denominator, and I add the top, and that's 192. And that does simplify to a whole number of 64 inches. So for 19 pounds of resistance, the band is 64 inches long. Okay. So for the guided practice for 1, 2, and 3, you guys can definitely do that. F of x, remember, is just a fancy term for y. So for 1, 2, and 3, you're going to switch x and y and solve for y again. And then instead of 19 pounds of resistance, now you're doing 13. So those are, you can do those. All right. And then next we have the inverse. We're going to find the inverse of f of x equals x squared. So if you can do this all by your lonesome, pause it. If not, just follow along. Okay, so instead of f of x, I'm just going to write y equals x squared, and then I can switch x and y. So this is x equals y squared. So I switched x and y, now I want to solve for y again. So I'm going to square root both sides. So I'm going to square root this side, square root this side. This is going to be plus or minus the square root of x, and then the square end is a square root, so I solve for the inverse. So if I wanted to use the notation, the inverse of f of x would be, well, technically right now it's plus or minus x. However, we do have that x is going to be greater than 0. Right? So if it's greater than 0, we just want the positive one. Okay. All right. And then we're also going to graph these. Okay. So when I graph them, let's see, we're going to restrict the domain for x squared. So normally for x squared, our line of symmetry is at 0, and we plug in 0, we get 0. We can plug in 1 and get 1. I don't want to plug in -1 because my x is greater than 0. So I'm going to take that away and maybe do 2. So when I plug in 2, I get 4. So that is for y equals x squared. So to graph that, I get, let's see, 0, 1, 1, and 2, 4. So we get basically this half of the parabola. When I graph the square root of x, let's see, numbers to use would be, I can plug in 0 and get 0. I can plug in 1. The square root of 1 is 1. I can plug in 4. That's a nice number to use. The square root of 4 is 2. And on your guided practice, you might just need to use a calculator because you're not always going to know what the nice numbers are. So if I did 2, the square root of 2, if I put that in my calculator, I'll get 1.4. All right, so when I graph that, I get 0, 1, 1, 4, 2, right about here. And so we have that. And that's the graph of that. And what's nice about all inverses is they're going to reflect on the y equals x axis. This is y equals x, where the y-intercept is 0 and the slope is up 1 over 1. So all inverses are going to reflect on the y equals x axis. Okay. You can also tell if a function has an inverse if no horizontal line intersects the graph more than once. So if we look at the parabola one, the inverse is not a function unless we restrict the domain. So we said that x was only positive. So we wouldn't have that one. We wouldn't have the negative side. So it would pass the horizontal line test. So for this one, we have to restrict the domain, and x is going to be greater than or equal to 0. Then it would pass. Right? For this one, it looks like a cubic or some sort of odd function with a positive leading coefficient. The inverse will be a function because the original function only passes through a horizontal line one time. Okay, so that's all they're saying right there. So for example 5, we're going to determine whether the inverse of f is a function. What we're going to do is we're going to graph f of x, and if it passes the horizontal line test, it does have an inverse. Okay, so again, the best way to graph these right now is just to find some numbers. We can plug in 0, 1, -1, things like that. So if I do that, when I plug in 0, 0 cubed is 0 times 2 is 0 plus 1 is 1. We're going to get 3. This one, when we plug in -1, so 2 times -1 cubed plus 1. We do order of operations, so we do exponents first. And -1 cubed means -1 times itself 3 times. So this would be -1 times 2. So 2 times negative 1 is negative 2. And then when we add 1, we're going to get negative 1. So if I graphed all of that, see 0, 1, 1, comma 3, negative 1, negative 1. So we have this shape that kind of looks like this. Okay. And if I were to draw a bunch of horizontal lines, or if I have a horizontal line, let's see, like that. If I move my horizontal line up and down on the graph, it only intersects the graph once. So this does have a inverse, and then we'll find it. So our original function was, if I change f of x into y equals 2x cubed plus 1. So I'm going to switch x and y. And so now I have x equals 2y cubed plus 1. And then we're going to solve for y again to find the inverse. So we subtract 1. We get x minus 1 equals 2y cubed. And then divide everything by 2. So I have x minus 1 over 2 equals y cubed. And then we're going to cube root both sides, because a cube root will undo a cube. So on this side we have y. On the other side we have our inverse, x minus 1 over 2. Okay, so when we graph this, again, you just want to plug in some numbers. You're not necessarily going to know what's nice for it to work. So we could plug in 0. If I plug in 0, I'm going to get, let's see, the cube root of 0 minus 1 over 2. So 0 minus 1 is negative 1 over 2. So we can put that in our calculator. It's basically negative 0.5, and you take the cube root of that, and so that's going to be negative 0.79. Okay. We can also plug in 3. 3 actually makes it a nice number. We have the cube root of 3 minus 1 over 2. 3 minus 1 is 2. 2 over 2 is 1, and the cube root of 1 is 1. Negative 3 won't be a nice number, but that's okay. We can put it in our calculator. So this is the cube root of negative 3 minus 1 over 2. So that would be negative 4 divided by 2. So that would be the cube root of negative 2. So when I put that in my calculator, I'm going to get negative 1.25. And if you need help with your calculator, I can help you with that tomorrow. Okay. So when we graph these, we're going to graph them on the same axis. So when I plugged in 3, I got 1. So maybe right about there. When I plugged in 0, I got a negative 0.79, which is a number between 0 and negative 1, closer to negative 1. And when I plugged in negative 3, I got negative 1.25. So maybe something right there. So it's going to go like that and like that. So, and then if we draw the y equals x line, it does actually reflect on the y equals x axis. Okay, so that's kind of how you do that, because your guided practice asks you to graph them. So it says find the inverse of a function, so you don't have to make sure it has an inverse. Find the inverse of the function and then graph the function and its inverse. So for number 5 through 10, you're going to change out g of x or f of x for y, switch x and y, and solve for the inverse. And then if you could do that, if you like to do the guided practice at home, if you could do that part at home, and then if you get frustrated by the graphing, I can help you with the graphing in class. All right, let's see, yeah. All right, and then another thing is, just like on the other example, graph it on the same x and y axis for number 5, and then have a different x and y axis, but graph the function and its inverse on the same coordinate plane. And then we have a lovely word problem. So pause it, see what's figuring out what's going on. If you can solve it by yourself, go for it. And then just check your answer as you fast forward the video. Okay, so we have National Football League tickets. and it's modeled by this formula. And so we want to write down what it means. So P is the average price in dollars, and then T is the number of years since 95. So for example, if we were trying to figure out the 2000 average price, then that T would be 5, because that's 5 years after 1995. Right, so we want to write an inverse model of this. So we're not going to switch P and T for a model, because that would be confusing to figure out what P and T are if we switch them. Right, so to find the inverse model, we're just going to solve for T. So right now, it's being multiplied by 35, so we're going to divide by 35. So we get P over 35 is equal to T to the 0.92. Okay, all right. And then we need to get rid of that 0.192 exponent. So if we had y equals x squared, actually, if we were in inverse land, if we had x equals y squared and we wanted to get rid of the squared, we would square root both sides. If we had x equals y cubed, we would, to get y by itself again, we would cube root both sides. Okay, so this is very similar, just very a little different. So in order to get rid of the 0.0192 power, we are going to take the 0.1092 root of that, right? Which basically means we are going to raise this up the 0.1 over 0.192 power. Okay, so let me explain that again if that didn't make sense. Okay, if we have x equals y cubed, right? We can take the cube root, or we can raise this to the 1/3 power. Okay, so x to the 1/3 is the same thing as the cube root, right? So for this one, we actually want to, instead of taking the root, that's not going to help us very much. So we are going to raise this to the 1 over 0.192 power. We're going to raise this one up to the 1 over 0.192 power. Okay? Because when we multiply exponents, or we're going to multiply these exponents, when we multiply, we're going to get 0.0192 times 1, and 1 times 0.0192. And so that just leaves us alone with t. Right, and then for this one, we're going to have, so when we actually put this in our calculator, when we do 1 divided by 0.192 in our calculator, we get 5.2. So you can check for yourself. So this is going to be P over 35 to the 5.2 power. Right? And I can explain that a little bit more in detail in class 2. All right, so now we have our inverse model, and that part is done for us. So we are done right there. And then for the next example, now that we have our inverse model, so let me rewrite that. T is equal to the average ticket price, or average price, over 35 raised to the 5.2 power. Okay. All right, so we want to know when the average price will reach 50, or what year the average price will reach $58. All right, so we're going to plug that in for P. So we have T is equal to $58 divided by 35 to the 5.2 power. So do 58 divided by 35, and then you usually have a y to the x button, or you can have this button. And so when you do that, and you raise it to the 5.2 power, you'll get about 13.83, which is approximately 14 years. Okay, so it's not in 14 years, but in 14 years after 1995. All right, so in 14 years after 1995, the average ticket price of $58 will be in 2009. So we take 1995, we add 14 years to that. So in 2009, the average price will be $58. Okay. All right. And then for guided practice, you're doing the same thing. It's just a little bit different math. You're still solving for t, so you want to find the inverse. So you're writing the inverse model. So you're solving for t, and then you're using that inverse model to know when the average ticket price will reach $25. Well, baseball is less expensive. Okay. All right, and that is the end of the lesson. I'll see you guys tomorrow.